Any questions on homework? Matthew.
Yeah, I don't have a favorite.
Two, can you tell me about it? Never mind. We can talk later. I posted some extra problems. Pay careful attention to them. You got it?
Yeah. Okay, it's want to use series test in terms of series for divergence. Sum from a of 1 to n of -1.
Yeah, you just need to talk out loud. Is it the one? Yeah, it's the one where all the time. It's not an alternate. So pay close attention to the problems I posted. They're not in the online homework, but it's just a general rule, I think. Most of you are freshmen. Good rule for you to learn now that if your professor sort of goes out of the way to give you extra things to look at, you got to pay careful attention to it. There's a good chance you might see something like it later on. I posted a page with 13 series on it. 2 of them, we really aren't equipped to deal with them until after today's class. And then I told you some information about the other 11. And I hope I gave you good information, but check it out. See if you agree with me. On the online homework, a lot of the times you're just asked, does a series converge or diverge? On the exam, you'll be asked to show why it converges or diverges. So it's not just going to be a 50-50 shot at getting the right answer and all the points. You're going to work through, you're going to say it diverges because of the divergence test, and here's my justification. Here's the limit. Calculating is 7, it's not 0, therefore it diverges. So keep that in mind. The process, more important than the final answer as far as grades are concerned. All right, you can see, just so you know, I'm recording this session. A person was unable to be here today. And I usually record Monday anyway because of the situation in my afternoon class. I don't record it usually here. But we'll let this cover. Our second exam is a week from Wednesday. Third exam, a week from Wednesday. Make sure that's on your calendars. We'll work hard this week. And then take an exam next week. All right, before we jump into the next section, I think it's section 6. Two more tests. I think the last 2 that we'll learn. The racial word test. But before we get into the details here, there's something we need to talk about. Probably seen it before. Factorial. Factorial is going to play a pretty significant role in the work that we do pretty much the rest of the semester. And so let's figure out what it is. A couple of ways I can define it. It's a function. It's a function defined on the natural numbers, the positive integers, and also 0. If you're a computer programmer, you might like this recursive definition of it. Says that n factorial, so remember it's a function. I'm going to take a positive integer, or at least a non-negative one, plug it in, The symbol for the function is the exclamation point. And what it's equal to is n times n minus 1 factorial. And 0 factorial equals 1. It's going to define that to be true. It may feel a little bit unusual to you, but it's essential. And if you don't trust me, ask your calculators what 0 factorial is. It'll tell you 1 as well. So basically, this says that to find the factorial of any integer, I need to know the factorial of the integer prior to that. And eventually, there's one of them that I know. And so I can call this recursively. For example, 3 factorial is 3 times 2 factorial. By the recursive definition, well, we don't know 2 factorial, but I know it satisfies that. So that's 2 times 1 factorial. I don't yet know 1 factorial, but I can use the recursion formula. And finally, I know that. So I get 3 times 2 times 1 times 1.
That's
Times
6.
6. Okay? That's factorial. And, I worked my way through that once, just like I did, and you see what's going on. We heard Will respond to it. Like, oh, yeah. So a non-recursive definition would say something like this. N factorial equals n times n minus 1 times n minus 2 times 3 times 2 times all the way down to 1. I don't really need, I won't write the 0 factorial that shows up. That's just 1. Not really necessary. So it's the product of the integers starting at the 1 we want the value for, all the way down to 1. And of course, we can ignore this 1 at the end. That's not going to affect anything here. So 5 factorial, 5 times 4 times 3 times 2. I could write times 1, or I could not write. It's not going to change it. 120. Okay. If you've taken a programming class, you probably one of the typical early exercises to write a program to compute factorial. And especially doing it recursively is an interesting process. And it's a simple one. You can learn how to do it with a simple example. So factorial is a really interesting function. It grows extremely fast. A long time ago, I got asked to write a computer program that had to process a bunch of data. I wasn't sure how much data to process. I just thought I would just write a brute force algorithm that could process everything. It turns out that in order to get this program to work, I needed to write a program that looped through statements 20 factorial times. Okay? Factorial shows up naturally in problems like how many orders can you announce the players on a basketball team, the 5 starting players? Well, the first one I announced, I could pick any one of the 5, right? And then I need to announce the second one. Well, one of them's already been announced, so there are only 4. And the principle says you multiply those. So 5 times 4, 20 ways to announce the first 2 guys. And then the third one, there's another 3, and I just keep multiplying. The answer is 5 factorial ways that you can rearrange 5 objects. It shows up naturally in lots of probability problems. So that's what led to me this. I need to write a program that processes data, potentially 20 factorial pieces of data. And so I just did it. Let me do the calculation here. On that. If I turn my phone sideways, I have a sign. So it turned out 20 factorial. Let's say my computer can process 10 million of them every single second. How many seconds does it take? So I divide by 10 million. 0, 0, 0, 0, 0, 0. It takes me that many. There are 12 numbers before the decimal. Seconds. There are 3,600 seconds in an hour. If I divide by 3,600, I get 67 million hours it would take. If divide by 24 hours in a day, makes 2.8 million days it would take, divide by 365 days in a year, 7,714 years, divide by 100 years in a century, take about 77 centuries for my computer to do 20 factorial things if it could do 10 million every second. And it never did stop. Factorial is unbelievably large. It grows faster than exponential. That's pretty much the fastest function we've seen to this point, exponential growth, but factorial beats it, as we will see here. And it shows up naturally. I gave you some examples. For us, it shows up naturally. I think we've probably worked on this in Calc 1. If you take a function like, I don't know, x to the n, and ask for its nth derivative, what do you think we're going to get? Well, every time we take a derivative, we peel a power down, right? And those powers gradually decrease. So we're going to get n, and then n minus 1, and then n minus 2. And in fact, if we take n derivatives, we've driven all the x's out of it, and we get the constant n factorial. And maybe you remember seeing that. I probably talked about it in Calc 1. I usually do. Don't remember if I did last fall in all 3 of my classes. But it shows up naturally in lots of different ways. And remember, 0 factorial is 1. It doesn't feel very intuitive, but it needs to be 1. There are really good reasons why 0 factorial is 1. And again, I know if you don't trust me, just plug it into your calculator, and then you'll feel really good about it. All right. So with that, it turns out we're going to see a lot of factorials. And a lot of the tests we already know, they maybe don't work so well with factorial, but there is one super powerful test. The test that we will use most often as we finish these chapters on series, the ratio test, which is just perfect for factorial. All right, so I think we're going to start with series that are non-negative, the terms are non-negative. And here is my series. I want to determine, does it converge or diverge? And maybe none of the tests we know resolve the issue for us. So I'm going to do a computation. We're going to calculate a limit. We've done that before. This is a little different. Going to take the limit of consecutive terms. The further term on top, the nearer term on the bottom. We're all in. We'll just take the limit as n goes to infinity. If there are 3 possibilities, because their terms are non-negative, L can't be negative, could be 0. If L is less than 1, it's impossible for it to be negative in this context. The series converges. Less than infinity. Step 2. If L is greater than 1, it diverges. And third case, obviously, if L equals 1, the test fails. We don't know what the series does. It may converge, it may diverge. We'll run another test. See if we can do that. I'm not going to prove it. It's not complicated. We basically, what we can do, if the limit is less than 1, the first case, then we can bound the terms of the series by a geometric series that converges. Okay, and then we can use the comparison test. We have this converging geometric series, which is greater. If you're curious about that, I'd be happy to talk more about it. We're just going to focus on using it. And so let's do some examples. Apply the ratio test. Start with the super simple one. N equals 1 to infinity. Let's do 0 to infinity. 1 over n factorial. Maybe one of the most important series of all the ones we've seen. But we don't know how to deal with it. The factorial is only defined on integers. So, the integral test would never, ever be a thing that we would use. If there's factorials present, we'd just ignore the integral test. Maybe we could figure some other tests out, but when you see a factorial, your very first thought should be the ratio test. Okay. If that fails, then we'll go to plan B. But it's not going to fail here. So take the limit as n goes to infinity. You ought to have a strong feeling that this series converges if you believe what I said about it. Factorial growing faster than all polynomials, all exponential functions, and it's in the denominator, and it will converge, as we'll see. So the n plus first term is that. The nth term is that one. Right? N plus 1, n. The limit as n goes to infinity by simple algebra. That becomes that. Now, properties of factorial. So the numerator is the product of all of the integers 1 through n. The denominator is the product, all of them 1 to n plus 1. So all of the factors in the numerator are factors of the denominator, right? And there's one extra factor on the denominator. So this cancels, actually, it cancels that factorial. And we're just left with 1 over n plus 1. And the limit of that is 0. See how that works? Factorials being products, we can just cancel out. One in the numerator, one in the denominator, cancel out all the common factors. And n plus 1, well, 0, that's less than 1. So we're in case 1, convergence. We're going to find out later that it actually converges to the number e. But we'll save the details for when we're ready to justify it. Questions? Matthew?
So, we know that we do the limit of an plus 1 over an.
Yep.
So, when we did that, we did 1 over n plus 1 factorial.
Yep.
So are we always going to do 1 over whatever in like factorial? Because it's like when I see a n plus 1, I think the plus 1 would be on top of factorial.
Okay, maybe I made my plus 1 too large.
Oh.
How's that? Good question. That's the n plus first term divided by the n. Part B. The ratio test will always fail for P series and similar series. And let's just do one not terribly interesting example. N squared plus 4 divided by n cubed plus n squared, I guess. Does that series converge or diverge? Do we know by other tests?
It diverges
And how would you prove
because
it?
of the degrees of the numerator and the denominator. The denominator is third degree, and the numerator is second degree. So that means it becomes similar to the harmonic series.
Absolutely right. It's very nearly a harmonic series. And because the difference in the degrees is 1, it needs to be bigger than 1 for convergence. So let's see what happens. L is the limit as n goes to infinity. And I get n plus 1 squared plus 4 divided by n plus 1 cubed plus n plus 1 squared. Now, I'm going to get just a little bit lazy here. I'll explain it carefully. Almost all the time, the formula that a sub n is a fraction. Not surprisingly, because it has to go to 0, right, for the series to have even a chance to converge. And so you're right, expressions that go to 0, a lot of times they're in fraction form. So rather than write this thing out immediately, I'm going to always write it like this. And flip that a, and I'll show you what I mean. So I need, this is a n plus 1, I need to divide by a n. Well, I can just do n cubed plus n squared divided by n squared plus 4. I flip that a n. I remember, I don't know where I learned about division, probably 4th or 5th grade, but my teacher drilled it into my head 60 years, well, not quite 60 years ago. When you divide by a fraction, you invert and multiply, right? We're just going right straight to that step rather than writing out the full thing like we did here, like the formula suggests. All right, the numerator, what kind of a function? If you multiply it all out, do it in your head, what kind of function do we get?
A rational function.
Okay, so you're one step ahead of me. I said the numerator
Or the polynomial.
of degree
2.
in the numerator, the whole numerator.
5.
5, degree 5. Everybody see it? The denominator is a,
5th degree polynomial.
yeah, so the limit as n goes to infinity is the ratio of leading coefficients, right? What's the coefficient of n to the 5th in the numerator? Can you do it in your head?
1.
Yeah, and in the denominator. And we get 1. Okay, so that's kind of glossing over. Is everybody okay with that? All we need, I mean, we see those common degrees, and that's easy to spot. And then we just need the leading coefficients. And in this case, it's easy to find them. You know, it could be more complicated, in which case we would just add in a few steps. What does 1 say for the ratio test? Well, we're not here, we're not there. Rats, the test fails. And it will always fail for anything that's remotely like a p-series. Okay, so when we see factorial, ratio test is our very first idea. When we see p-series polynomials, then we never want to do the ratio test. Probably the comparison, limit comparison. Will told us he thought it diverged, and we could actually prove it with limit comparison with the harmonic, just like Will said, 1 over n. That would work out just fine. All right. Let's try this one. Column C. Summation 2 to the n times 2 to the n over n factorial. So partly here, I want to justify what I said earlier, that factorial grows faster than any function we've seen before. Before today, the exponential functions would be the fastest growing functions. So we see the factorial here, and our very first thought is to use what test?
The ratio.
The ratio test. Yeah, I'll take the limit L as n goes to infinity, the n plus first term, times the reciprocal of the nth term. That's our shortcut. If you don't like that shortcut, then write the whole thing out. Do whatever works for you. That weird looking thing is an N. All right, so what happens? We get this n plus 1 over n. Like we'll group the polynomial pieces and then the exponential pieces and then the factorial and see what happens. Everything is multiplied together so we can just break it into those factors. So I get an n plus 1 over n. I get 2 to the n plus 1 over 2 to the n. And I get n factorial over n plus 1 factorial. You can do it when we're multiplying. You can't do that when we're adding. Okay, do you follow me? So we learned in Calc 1, Chapter 2, the limit of a product is the product of the limits. If they all exist, what's the first limit there? N plus 1 over n.
It's 1.
1. What's the second limit?
0. No. Yeah, it's 2.
2. It's just the function 2. Cancel out all the common 2's, and 1 survives in the numerator. And what's the third one?
0.
Yeah, that's the one we did over yonder. We get 0 less than 1, it converges. So the ratio test settles the issue. So the fact that it converges means the denominator is growing faster. Notice in the numerator, we have more than exponential growth. We have exponential times polynomial growth. So like we're speeding it up even more, but the factorial just kills it. It doesn't even matter what power. If this is to the power p, then we would have n plus 1 to the p, we would have an n to the p. And that limit would be 1 to the p, it would just be 1. It doesn't even matter what the degree of that polynomial power is. Factorial, pulling the whole thing, the limit down to 0, which means it's forcing that series to converge. Any questions? So I haven't looked at the online homework yet. The problems in the book get pretty exotic, pretty fast. So let me see. Why did I take that website? See if I can read it. My camera upside down for a second. I will call it part B. So summation 2n factorial over two n to the pi, that looks to me like. It's actually 2n to the n. Not that it matters. Either one. Okay. So I've been touting factorial as an extremely rapid growing function, the most rapid we've seen, but this problem is going to challenge that just a little bit by combining exponentials and polynomials. That is, can you see in the denominator the function n to the n? where both the base and the exponent are variables. Okay? We may discover that that has the power to outgrow factorial. We'll see. Actually, I'm not 100% sure how it's going to work out. We see the factorial makes us think what test right off the bat? Ratio. Now, it could fail, but it's always going to be our go-to test when there are factorials involved. If it fails, no big deal. We'll go back and find another one. If the book, or if I am asking you to analyze it, we'll believe that it's analyzable. But notice 2n factorial, the exclamation point outside the 2n means 2n times 2n minus 1, so on, 2n minus 2. Eventually we get down to n minus 1, and so on. As opposed to 2 times n factorial, that's just 2 times n minus 1. So having that 2 inside the factorial, the parentheses, makes a big difference. It's like a hyperfactorial in the denominator. All right, and then we have 2 times n plus 1 to the power n plus 1. And then we reciprocate the formula and multiply by it. So there's a lot of stuff going on there. Some of it we've not seen before. We need to be a little bit careful, but we'll deal with it slowly. So let's do this first. On the previous examples, I didn't give you a lot of detail. I showed you what's true, and then I explained why we could do it, and nobody asked any questions. So we'll call it good. This one's, there are just some subtleties here. And so I'm going to take it a little bit slower. This guy right here, like as soon as I get down to 2n, all the numbers below that are going to cancel. But it takes me a little bit to get there. That is, this is equal to 2n plus 2 times 2n plus 1. And then we're down to 2n. That's the numerator here. 2 times n plus 1 is 2n plus 2. And we're taking its factorial. So we're starting at 2n plus 2 and then peeling them off. And I wrote just enough to get down to the ones that show up in the denominator. All right? And then we've got our 2n factorial. I'm going to push it over here with the factorial expression. So I've accounted for all of those. Those and those. I've got them down below. And we need the rest of it now. Well, notice in the numerator, I get 2 to the power n, and then I get 2 to the power n plus 1. What happens with the 2's? I have one more in the denominator than in the numerator. 2 to the n on top, 2 to the n plus 1 on the bottom. Then I get a very interesting thing. I get n to the power n over n plus 1 to the power n plus 1. And I believe everything is accounted for. Questions? Are you with me?
Yes.
What should I do next?
So you can cancel the 2n factorial.
Absolutely. I'll do it in blue. Gone, gone. That's the bad one. 3 point. It was supposed to be blue. Take the 1/2 out. Let's do that. We'll focus on what's left. Let's factor the 2 out of that, just for the fun of it. And then I have a 2n plus 1. And then I want to combine these, like with a single exponent, but the exponents are different. I have one more power on the bottom. If I pull one of those off, then I would have the power in, numerator and denominator. And so I'm going to pull one of them off. Well, the thing that's raised to the n plus 1 power is n plus 1. There's the extra one. And then I have n over n plus 1. The power n. I can cancel those n plus 1s. So it all comes down to what this guy is. Let's pull him out and take a close look. That's the not obvious limit. Does anybody know what it is? We've seen it.
It reminds me of the limit for E.
It does, but it's actually it's upside down. So good spot, Will. Let's write it like this. Let's put it down in the denominator and then flip that thing over. N plus 1 over n. Power n. So I reciprocated it twice. Means it's the same thing. It looks different. Now, what do you think, Will, or anybody? What's that limit? I think we can compute it now. Limit of the numerator is 1, no problem there. What's the denominator? You can write that as 1 plus 1 over n to the n.
So the limit, it says 1 over E.
Yeah, that's E. We remember, if you take careful notes in Calc 1, go back and you'll find that result boxed up. There's probably the word memorized right next to it. I told you we'll run into it every now and then. And here it is showing up. All right, so this is like working on this guy right here. So let's put it all together. I have 1/2. And then this guy is 1 over E. And what's left here? Oh, notice there's a 2 to cancel our 1/2 out. I'll just write a 2 inside here. But then as n goes to infinity, what is this thing? He's the only guy left. What does he do?
Infinity.
It goes to infinity. Our limit is greater than 1. Therefore, this series diverges. So n to the n beats. It is faster. Factorial. That's one of our lessons here. You know, but in the defense of factorial, I teach probability. We use factorial all the time here. N to the n is not a very natural function. We don't see it very often. It's not the result of any sort of natural physical process, whereas factorials are really useful, as I described earlier, and ways we'll see in the future. Any questions?
So
Matthew. Let's go with Matthew.
And so when you went to the first time you looked at the limit, the second time you looked at the limit, you got basically I was wondering where your 2 in
Okay.
the on the right side on the 2.
Here.
So go up further up. All the way to the first. Yeah, where did that 2 go?
Where to go?
Yeah.
Okay, so right here I have 2 to the n, right? We learned way back yonder, a b to the n is a to the n, b to the n. Yeah. So next time you see your high school algebra teacher, make sure they emphasize laws of exponents, they seem so trivial when we see them in high school, but we use them all the time. Matthew, are you good? So that kicks out a 2 to the n. And then out of here, I get a 2 to the n plus 1. So these all cancel, but this one survives, one of them. And there it is. Well,
So n to the n beats n factorial, does 2 times n in the factorial, that be n to the n?
no, in fact, notice what we have here is we have actually double n factorial. I wrote it out here, I erased it. But this is like double n factorial. This 2 is not trivial, right? We stack a whole, n factorial is a product of n numbers. 2n is the product, 2n factorial is a product of 2n numbers. Twice as many numbers in the factor. So it's growing at them. And all of the new guys from n plus 1 all the way up to 2n, they're bigger than all of those. So it's like, it's this huge, monstrous function. But that function beats it. And I don't think we need the 2 to beat it, right? Because we've got that infinity. I don't think if you took the 2 away that change that. But I don't think. Any other questions? Matthew?
Yeah, so at the very end, we had to find the limit of n over n plus 1 or the n.
Yes, we had to find it, not at the very end, but next to the end.
Right. I guess, why do we have to do that? Do the limit of the left side, that was the infinity, correct?
Okay, so I think Matthew's question is looking here, like he thinks this is manageable and this guy's going to infinity. So why do we even need to know that? I think that's a fair question. I guess it doesn't hurt to know it. If this went to 0, then we would have infinity times 0, which is an indeterminate form. So at the very least, I need to convince myself it's not 0. Once I see what's going on here. Okay, until I see that, then this guy's very much involved in our answer. Okay, good question. Any others? All right. So that's the sort of problem that is in the textbook. They're all, I don't know, they're gimmicky, the ones in the textbook. So I took a picture from a book I used to use, thinking there might be better problems. Let's try this one. I think we're down to E. Actually, reasons to not talk about limit changes. We'll talk about that one eventually, the one line.
Is it because of the trig function?
Yeah, and it turns some of the terms negative. Oh, I know what we need to do. The root test. So our final test. It's very much like the ratio test. Here's my series. I need positive terms here. You'll see. It's crucial here. Then we're going to calculate L, the limit, as it goes to infinity, the nth root of the generating formula. A sub n. I was going to mention over here, like maybe someone has the question, you didn't ask it, but if this exponent is a particular number like a cube, then we always slip the limit inside, figure out what's going on, and then cube it. Like, how come we can't do that here? Go inside, get a limit of 1, and then raise it to the power n. And maybe you can see the answer. The answer is that the power depends on n. It's not a constant. And so we don't have any theorem that says we can like ignore these ends and not those when we're calculating the limit. So if this were a 5, what would this limit be?
It would be, 1 to the 5.
1 to the 5th, it would just be 1, right? It's a simple limit when it's a constant. It's when it's in that it's a little more interesting. Same thing here. I can't slip the limit inside because this is the nth root. It depends on n. The conclusion is exactly the same as the ratio test. If the first case, L can't be negative, it's strictly less than 1, it converges. Second case, if L is bigger than 1, it diverges. And third case, guess what? If L equals 1, what do you think? Test fails. Go find another test.
So do we use the root test when the ratio test fails?
I doubt it. Nth roots are complicated. You really don't know any like nice algebra they satisfy. So the only time we're going to use the root test is when our formula has the variable in its power. And then it's going to work out slick. Here's an example. Summation. 1 plus 1 over n to the n squared. All right, the formula has some algebraic formula raised to a power that involves n. So chances are, when I take the nth root, it's going to work out pretty nice. Okay, let's try it. We're going to use the root test. And so we're going to calculate L, the limit is n goes to infinity, the nth root of 1 plus 1 over n to the n squared by the properties of exponents. That is 1 plus 1 over n to the n squared times 1 over n. Raise an exponent to an exponent. That nth root is the 1 over n exponent. When we raise an exponent to an exponent, our 8th grade math teacher told us you multiply the exponents. N squared times 1 over n is n. N goes to infinity. 1 plus 1 over n to the n. Does anybody know that limit?
We just talked about it.
Yeah, it's e. And e is
Greater than 1.
greater than 1. So
It diverges.
diverges. All right, so this guy right here, strong suggestion that the root test is the way to go. At least it's the one we're going to try first. It could still fail. But interesting thing here, what happens if I change this plus to minus? Let's crack it through. Now what's the limit?
It's 1 over e.
Yeah, it's e to the minus 1, which is 1 over e, which is
Less than 1.
less than 1. So now just changing that sign makes it work. If we're careless, you would say, well, as n goes to infinity, the base goes to 1. True. 1 to any power is 1. So we would say the terms don't go to 0. They go to 1. So by the divergence test, it diverges. But when we use that logic, we're ignoring the things we learned about where did I write it out? I wrote it right here, right here. Things we learned about this particular limit right here. And here, get the power of the square. If I take the square away, the terms go, even if I know the limit, it goes to 1 over e, that's not zero, divergence. It's the square that has the power under the root test to get us a good value. All right. So later on, we're going to modify the ratio test, but other than that, we're done learning tests. Like, I think it is, we end up with 10 of them, so it's not like we don't have a pretty good arsenal. But we're done. There are no more new ones other than a little tweak of the ratio test. We're going to call it the ratio test for absolute convergence. We're going to apply it to an alternating series. All right. See you Wednesday.
Yeah.